All right, so for those of you who can't really find a chair, I'm not too sure about what's going on. My best guess would be just try and make it work in the back, if that's cool with you guys. Unfortunately. Otherwise, we're gonna go ahead and get started. This is the 6 p.m. Chem 2045 final review for Dr. Hyder's lecture. And I'm your SI leader, Katie. This is gonna basically run through the outline and some practice questions to review the material we've had, chapters 1 through 10. If there are any straightforward questions, raise your hand and I'll try to answer them throughout the review. If there are any more detailed questions, I'm going to leave about 15 minutes open at the end to try and answer those questions, okay? So let's go ahead and get started, and I'm going to try, yes? Yes. That's the handout online. You don't have to print it out. It's just the guide which we're going to use. So this is on ucfsi.wordpress.com. All right. So again, we'll start this as a run through some of the material as we go along. As I ask you guys the question, I am hoping for a response. Okay? Not everyone has to respond, but I'm hoping we'll get some responses. So with the course, we started out with matter and the breakdown of atoms and molecules and how that worked with scientific approach to knowledge. A good hypothesis is what? Thank you. A good hypothesis is falsifiable. We want to be able to deem that it is incorrect. If we cannot, then we can assume that it's true. Through that, we have experiments, and with our experiments, we have two types of observations. They're qualitative and quantitative. What is a qualitative observation?
As in, like, looks, for instance, it's luster, it's mass, not really mass.
So, right, luster, mass, it's more of description is what we're going for. How about quantitative? Numbers, measuring numbers. And then we went into the differences of laws and theories, summaries. Laws, a summary of the observations, which cannot be violated and allows you to predict the future observations, whereas theories are principles that explain the facts of those laws. We then moved through our states of matter. We had 3 different kinds of states. We had solids, liquids, and gases. If it has a fixed volume and a fixed shape, what is it? Solid. How about if it's a fixed volume and an indefinite shape? Liquid, thank you. Indefinite volume and indefinite shape would be gas. From there, we had a breakdown of mixtures and pure substances. If we go into pure substances and it's only made up of one element, what is it considered? It's just an element. If it's made up of more than one element, what is it considered? Compounds, which can also be seen on our nifty little chart. We also have mixtures, which if it's uniform throughout, what is it considered? Homogeneous. Thank you. And if it's not uniform throughout, what do we have? Heterogeneous. We then had a breakdown of properties. If a change occurs and the composition does not change, what kind of change is this? Physical. Be careful with this. This strictly has to deal with changes in the state, so as in solid, liquid, and gas. If we have a chemical composition change, what is it? Chemical. This is common, seen with burning, bleaching, rusting, oxidation. So for our first question, we have when gaseous water becomes a solid, what type of compositional change is it undergoing? Deposition. Which of these undergoes a chemical change of the following? We have sublimation of dry ice into carbon, heating sugar of caramel, and mixing an acid and base. So we have a vote for C. Are any of these others also a chemical change? Good. So we also have heating of the sugar for caramel. So B and C are both chemical changes. Sublimation of dry ice is still carbon, so that will just be a physical change. The course then moved on through measurements. Make sure that you understand your prefixes and how to go back and forth between them. With measurements, we also had to deal with accuracy and precision. Know the difference between those. Accuracy is how your numbers relate to the actual value of a measurement, whereas precision is how your measurements relate to one another. Okay? For significant figures, we had 0 rules. We had 4 rules in particular. We'll use the slide over here. So if a 0 does nothing but set the decimal point, are they significant? 0 setting a decimal point. So as in 4,500 or 009. Are those zeros significant? No, not significant. If 0 within a number, is it significant? So, example 373.08, and that will be significant. Yes. How about trailing zeros?
No.
They are not significant unless what happens?
The decimal point is at the end.
What was it?
Decimal point is at the end.
So we either have a decimal point at the end, as in 800, or if we have $8, this would also be considered significant. Exceptions, these are significant. And the last rule for significant figures we have is exact numbers. How many significant figures can they have? Infinite. So they have an infinite number of significant figures. Is everyone okay with significant figures? All right. So in terms of multiplication and division, we use the lowest number of significant figures given to us, and for addition and subtraction, we use the lowest number of significant decimals given to us. Okay? Moving on, we had atomic laws. Definitely review these. They're very important conceptually. We have law of conservation of mass. We had definite proportions and multiple proportions, and also atomic theory. One way to remember the difference between definite proportions and multiple proportions is that definite proportions is basically saying that no matter what, your compound is always going to be that compound. If we have C2H4O, it's always going to have 2 carbon, 4 oxygen, or 4 hydrogen and 1 oxygen. That's never going to change. As in multiple proportions, we are looking at how the elements combined. So we have C2H4O plus water. We're going to look at how those combined with each other, not just how they're composed, okay? So one's an addition, where the other is always just a compound, okay? That's what we're looking for. In terms of atomic theory, remember it's a theory. So can a theory be violated? Yes. So be careful understanding that even though we have our rules for the atomic theory, they can be violated, okay? Moving on, we have isotypes and ions. What is changing in an isotype? Neutrons. So we have a change in the number of neutrons. And ions, we have a change in the number of what? Positive ions are considered what? Cations. And how about negative ions? Anions. For conceptual-based question, we have a true or false. Protons and neutrons contribute most of the mass of an atom. True. How about electrons? They're negligible, they don't entirely amount to much when it comes to the mass. All right. For carbon, if we have the symbol of 14 carbon, what do we know about it? So we have that the 14 is atomic mass. And what is the atomic mass made up of? Again, we have our protons and neutrons. From that, what typically does not change in an atom? So our protons will not change. So with our question, how many neutrons, protons, and electrons are we expected to have?
14 in total.
So 14 total for our protons and neutrons, but how many neutrons are we expecting to have? 8, because how many protons do we have? 6. And with that, how many electrons should we have? 6. So 8 neutrons, 6 protons, 6 electrons. We also then went over Avogadro's number, and that's considered 1 mole. We'll get to a few of those calculations in a moment. We also then had different types of chemical bonds. If we have an ionic bond, what elements are bonding together? So we have a nonmetal and a metal. How about if it's a covalent bond? So a metal with a non-metal with a nonmetal. And finally, if we have a metallic bond, what are we bonding together? Metals and metals. From this, we have a breakdown to name these types of compounds. If we have an ionic compound with a metal and only one type of cation, how would we name it? What goes first?
The name of the metal.
We have the name of the cation, or the name of the metal. And what comes second? Base of our anion, or nonmetal, with "ide" at the end. With that example, so our most basic, if we have NaCl, what's its name? Sodium for our cation. We have our chlorine anion with an "ide" at the end. We have chloride. If we have naming for ionic compounds with a metal that has more than one type of cation, what do we begin with? So in this case, we're going to have, again, our name of cation. We're going to also end with the base of our anion and what goes in our parentheses. Our Roman numeral to designate what? So in this case, if we had a chromium and 3 bromide, what might we name this? Chromium 3 bromide. All right. Moving forward, if we have naming molecular compounds, what do we start with? I heard it. What was it? Prefix. Thank you. Speak up, guys. I can't always hear you. So for both sides, we're going to start with our prefix. And in the first half, we're going to have the name of what? Our first element. And our second one, how are we going to form that? So we have the base of our second element with "ide." Remember, in a molecular compound, we're dealing with what kind of atoms? 2 nonmetals. So for an example, if we have NO2, how are we going to name it? We have nitrogen dioxide. Naming of binary acids, what do we begin with? Hydro. We have then what? So our non-metal base with the ending IC. And we'll just round that off with acid. If we have oxyacids, what do we begin with? So we have the base name. And then we can have 2 different kinds of endings for oxyacids. If we normally have the ending "ate," what does it become? Ic, IC. And if we have "ite," what does it become? Us, OUS. And again, it's an acid. We'll just end that with an acid. And then for the difference in acid, if we have a binary, it looks sort of like HCl. And how do we name that? Hydrochloric acid. And if we had HNO3, it'll be nitric acid. So then if we have H2SO3, it's the other one. Thank you, sulfurous acid. Commonly, oxyacids will be associated with polyatomic ions, which the next little chart here, definitely make sure you memorize this. It'll help you with naming, it'll help you with charges, it'll help you with your Lewis structures later on. Definitely very important. Okay? Yes?
When naming molecular compound, how do you determine which element comes first? Is that electronegativity or?
So for your molecular compound, the name that comes first is how it's written in the formula, typically.
Okay.
So in this case, with nitrogen, that's why nitrogen comes first.
Okay.
So, yeah.
Do you tell us like which formulas will be included on the test and which ones we have to memorize?
I'll go over that as we go through. There's a section for some of that. Yeah. So, real quick, let's go through a few practice problems. For naming, yes?
Are you going to post this like after you're done?
I plan on posting the answers, yes.
And is there a way you can like turn down the lights? I don't know if that's still. I mean, some of the lights, but it's really lights.
I'm sorry, I can't really,
All right.
yeah. All right. If there's something you need for me to like rewrite over, I can go over that later. Yeah. All right, so real quick, let's just run through some of the naming. If we have cobalt 3 phosphate, how do we figure that out? So I see some hands we're going to cross over. So our charge for cobalt has been given to us. How about our charge for phosphate? So we get -3. If we cross those over, we would just have 3 and 3. So our most basic number, we're just going to end up with B. All right. Same function if we have lithium nitride. Nitride. So what might that look like as a formula? So LIN, again, for the ionic formulas, we're going to be mainly looking at our charges, okay? How about sulfur tetraoxide? So be careful, that's again working with our prefixes. We're going to get SO4. In this case, is it ionic or molecular? Molecular. This is molecular. Yes?
Why is lithium
It's a good catch. Thank you. Again, make sure you do your math. Cross them over, okay? Moving forward, if we had hydroiodic acid, what are we going to get? So H and I, they have the same charge opposing, so we'll just end up with 1 and 1. And our potassium sulfate. So this again, our polyatomic ions. So our sulfate, we're going to get SO4. And our charge for that is 2-. And our potassium is K+. So how many potassium should we have? 2. And SO4. Filling out with acids. If we have nitrous acid, what are we going to have? So I heard it, HNO2. And our silver 2 fluoride, we have a transition. So Ag2 plus fluoride will end with AgF2. And if we want to go backwards with the magnesium, or no, we're still going forwards. Magnesium bromide, what are we going to have? So I heard it, we're going to get C. And if we want to go with our naming, LIF. So we get lithium fluoride, and is this ionic or? Yeah. And FeCl2, iron 2 chloride, because iron is what? Ionic with a transition. And then our K2SO4 again. And what kind of compound is that? Is it a polyatomic, or what do our polyatomics go forward? Are they molecular, ionic? Are they? In this case, we're going to get ionic. All right. Because, again, what is a molecular compound? 2 nonmetals. HBr, what are we going to get? And what naming system is that? So our binary acid. How about NaNO3 with 6 waters? What do we consider the water? So it's a hydration. So in this case, our NaNO3 is going to be named just like it normally is. So what's the name for that? Sodium nitrate. And if we have a hydrate, this is going to follow our prefix system, which would just be hexahydrate. Hexa being our 6 waters, okay? And finally, our H2CO3 is what? Thank you, I heard it. It's carbonic acid. And in this case, that's an oxy acid. So moving forward, we got some more of our calculations and conversions, getting more into our stoichiometry. We have percent composition, our percent yield. These will be important. All of these will be important equations for the exam. In that case, we also have molarity, dilutions, mass to mass, which also incorporates our moles to moles conversions. Okay? What is a limiting reagent?
Part of the reaction with the least amount of moles or parts.
So the reactant with the least amount of parts. How about our excess reagent? It's what's left over. So moving forward, let's go through some of these practice equations. If we want to get the percent of oxygen in a compound of phenol with your formula has been given to you, how would we figure this out? All right. So we want to find the mass of the whole compound, also known as our what? Our molar mass. So long way is going to look something like this. And these numbers are found where? These are found on our periodic table. Now, if we multiply this entire thing out, we're going to get 94.2 or 12 grams. And we want to find what percent? Oxygen. So in that case, we'll divide the total weight of oxygen by the entire weight of the compound. And in this case, we get something that looks like this. So which percentage is closest? 17%. Is everyone okay with that? Our next question is a question that goes along with finding the percentage of the mass and being able to find that within another sample, which is similar to our what law? Our law of multiple proportion, or definite proportions, okay? So the percent is always going to be the same no matter how much we're starting with our sample. So in this case, what is the total mass of our first sample? How do we find that? So we just add what we're given. So in this case, our 1.65, 2.57, it's going to be, in this case, that's 4.22 kilograms. And then we want to be able to find the percentage of each of these compounds within the sample. So again, how do we do that? All right, thank you. So the mass of 1 over the total. 1.65 grams of magnesium in this case over the total times 100. For this case, we'll get 39% magnesium. And since we only have 2 atoms, what's the percentage of the other one? So subtracting from 100, we get 61% fluorine. In that case, we can say that the percentage is always going to be the same. So in the case we have 1.32 kilograms for our magnesium. And if we want to use that as percentage, we get 100 kilograms of the total sample divided by, in this case, we'll use magnesium again. So if we multiply this out, 3.38 kilograms for our total sample. And if we want to find how much fluorine, we have to take what we got for our total sample so our 3.38 kilograms of magnesium fluoride times our 61 grams of fluorine in every 100 grams of the sample, or kilograms. And again, if we multiply all this out, will it give us the mass of our fluorine? Yes. So we get 2.06 kilograms of fluorine. All right. Yes. It. So there's also the equivalation. That's fine. That will work as long as you keep the right totals together. Okay. Yeah. I believe so. Okay, so definitely review the laws and how to figure those out. Again, it'll help you be able to do some of your stoichiometry problems, okay? If we're all good, we'll move on to the next question a little slower. So in this case, if we want to find how many moles of nitrogen gas are in 5,000 milliliters, and we've been given our density. So what do we need to do?
We can turn that into mass since we have the density.
Right, so we turn this into mass since we have our density. We'll need to convert our milliliters to liters. So in this case, in general, this is a very important conversion. So if you don't already know your milliliters or your milli to the standard unit, definitely memorize that. And then we'll use our density, which is 0.765 grams over a liter, to determine our total mass, which then if we want to get moles, what do we have to do?
Divide that by the molar mass of nitrogen.
So we'll divide our molar mass of the nitrogen, and we'll get 1 mole up here. So that'll give us 2,730 moles, so which is, in this case, C. Okay. And then if we want to further break this down, again, we're finding our molar mass of glucose for the next question. So if we just, yes? So in this case, we're just using N. So we're just going to use a single nitrogen, okay? Yeah. So in this case, again, if we're just finding molar mass, we just have to find the molar mass of each component from the periodic table and multiply it by how many are in our formula. So in this case, it gives us 180.1 something grams. And in that case, we'll get B. So if we're breaking it down, we're going to use that in 13. So if we want to find how many moles are in 25.87 grams of glucose, we're going to use our molar mass. Sorry. So yes, it is N2. In this case, we're just going to use N.
How would we know on the test though?
So typically, we're going to want to use N2. When I pulled this question, they were just using nitrogen. So it's just from where I pulled this question. Generally, we're going to use nitrogen as a diatomic, okay? Just to clarify. If we have the same question on the test, use N2. the answers should be adjusted for N2.
And then argue.
Yeah. Okay, so again, we're going to go back and find our moles of glucose. So how will we function that conversion? We'll take what's been given to us. And convert it to moles. So again, we'll get what we want on top and divide by what we already have, which in this case, which will give us 0.69867 moles, which relates most to C. Okay. And in terms of significant figures, if it's not directly asking you for significant figures, just go with what's been given to you in the answer bank, okay? When taking moles from question 12, if we want to find atoms, how do we find atoms? This is where we're going to use Avogadro's number. We're going to take our 0.699 moles, and in this case, Avogadro's number is going to go on top to give us the number of atoms per mole, which, if you multiply this out, should give you 4.2093 times 10 to the 23rd atoms. Or if we are technically considering this as glucose, what is this considered? Instead of atoms, it should be molecules. So that most relates to A. Is everyone comfortable after breaking that down? All right. Moving forward, we have a chemical equation where 23.5 grams of oxygen, in this case, does specify we're using diatomic oxygen, which is correct. How many grams of carbon dioxide are produced from the equation? So what should we do first? We need to balance first. So if we want to balance this, in this case, since the easiest way would be to look at our carbons, since our carbon is the main structure for only one component on both sides. In this case, we're going to get this is our balanced equation. We'll go over balancing a little more in just a moment. So with our balanced equation, what should we start with? So find out how many moles of oxygen we ended up using. So from our given, again, to find our moles, be careful, again, we're using diatomic oxygen. So in this case, it is 2 times the molar mass of oxygen. Now what do we have to use? We need to use our coefficients. So in this case, what is our coefficient ratio? 4/7. Because we want to get the moles of carbon dioxide, so that should go on top, where what we already have will go on bottom. And again, to get our mass, we'll use the opposing conversion, where our molar mass goes on top for our carbon dioxide, which is 44.01 grams per mole. All right. Following that through, that gives us 18.46 grams. Which, in that case, most relates to answer B. Question number 16 is fairly similar, except in this case, what we're answering is what is our limiting reagent. In this case, this is not necessary. What we're just looking for is what limits our creation of water, okay? So in that case, we still have to balance our equation first. So if we balance this out, our equation will look like this. And in terms, we want to find the moles and ratio that out again. So we'll take what we started with, convert those to moles. Again, we need to use our mole to mole ratio. So for our first one, what goes on bottom? Moles of what? So we started with oxygen, so the bottom will be oxygen. And we want to find our water, so again, that will go on top. And to find mass, our molar mass will go on top, which in the end will give us 9.12 grams of water. In opposition, that will give us a molar ratio of 3 to 1. And our ending will look fairly similar. So from our calculations, our oxygen gave us 9.12 grams of water, and our C2H5OH gave us 38.01 grams of water. So in this case, what's limiting? Our oxygen, because it's what's given us less. Are we all okay with that concept? All right. Moving forward, we'll work a little with a question on molarity. What is the equation for molarity? So we get moles over liters. In this case, do we have liters? No. So we'll have to convert our 98.4 milliliters. Again, I get 1 liter over 1,000 milliliters. If we want to write out how this would typically look, our 0.678 molarity will be equal to an X number of moles over our 0.0984 liters. If we multiply those two together, that gives us 0.066 such moles, which in this case is identified in A 0.0667 moles. And if we want to move forward with solutions and we'll work out a dilution problem, that's number 18. So what does a dilution problem equation typically look like? All right, so some people like to do mad dog, vicious dog times mad cat, vicious cat, which the D standing for the diluted, C standing for the more concentrated, or just the fact that we're equivalating the two. So in this case, we're starting with 0.521 molarity in the volume of 79.6 liters. Do we have to convert any of those? No. As long as we're working to get the same thing on the other side, we're just fine. So we have 113.7 liters. So that gives us X molarity. And then divide both sides by 113.7 liters. That leaves us with our X being equal to 0.3647 molarity, which in this case is C, if we round. And if we want to get our molarity of a solution, again, it's working our molarity problem forward. So what do we have to do to our lithium chloride? Convert to moles. So our 54.6 grams, and again, our mole conversion of 1 mole over its molar mass, which is 42.39 for lithium chloride, and that gives us 1.28 moles. And if we want to find our molarity, we have to also have liters. So our 425 milliliters, again, we'll have to convert to liters. And we get 425 liters, or 0.425 liters, to be clear. And our molarity is just the division of our moles with liters. And that gives us something that looks like that, 3.0305 m, which in this case for 19 gives us the answer of D. All right, are we all comfortable with stoichiometry and conversions? Okay, so in terms, we also have to know the difference between empirical and molecular formulas. Remember, empirical is the lowest whole number ratio, whereas in your molecular formula, we have to use all of its constituents, which in the naming reason, that is why we have to use prefixes, whereas empirical is for ionic, whereas molecular is for molecular compounds. If we have our molecular formula, we just have to be able to know how many constituents we have to multiply this by, and that's given by the total molar mass divided by the empirical formula's mass. And so if we're moving forward, in that case, what should be the empirical formula of our C6H18 9 nitrogen? So we can divide all of these by 3 to get our lowest whole number ratio. So again, that gives us C2H6N3, where if we find the entire molar mass as well, that also constituents for answer D for question 20. Right? So we can't quite see it too well here on the printout, but definitely go over solubility rules. That's important going forward because we have different kinds of reactions. In that case, if we use molecular ionic equations, we're going to need to know what becomes a solid, or if it doesn't become a solid in that case. So to run through how to write these, if we use the example of adding iron nitrate together with sodium hydroxide, both of these in this case are aqueous. Our molecular formula should look like our stereotypical balanced equations, although we don't really have to balance this to break it down. And in this case, if we're switching our constituents, our iron will then combine with our hydroxide, and our sodium will then bind with our nitrate, which in terms of our solubility rules, which of these should form a solid? Our iron hydroxide. In the case of our nitrates, it should pretty much always be soluble, okay? Doesn't really matter what it's combined with. So if we want to break this down into our ionic equation, what should that look like? What should we have for pretty much all of our compounds? So they separate, or the fancy word we like to use is dissociate. So our iron becomes iron 3+, our nitrate is a negative. Our polyatomic ions are still ions, so those will stick together. So our reactant side will completely dissociate. How about our product side? We have to keep our solid together. And our sodium and nitrate will remain out of solution. So from our complete ionic equation, what should our net ionic equation look like? So I heard it. So on our reactant side, we have our Fe and our OH, which in that case gives us the solid on our product side. What are the other ions considered? Thank you. Spectator ions. So from what was crossed out, in that case, we have our sodium and our nitrate. Yes?
For the third bulletin, you put 3 in front of the OH, or you just supposed to be like that?
You can balance it. It's fine. However, in this case, if we just add the hydroxide ion, we should know that we'll end up with 3. Okay. So our next question is forming just between 2 singular elements, which is aluminum and sulfur. We can determine how these are going to form, one by charges. However, we can also use our Lewis structures, which give us charges. So in that case, what should our end product look like? So sulfur is also on our list of solubility rules. And if we're working with sulfur and aluminum, should our compound be soluble or insoluble? It will be soluble. And moving forward, we have to balance our equation. In this case, do we form a solid or liquid or is there anything insoluble going on? Yes.
How do you get that as a soluble?
So that's a good question. Hold on, I'm trying to. Typically because of the trend. You could also argue that the aluminum makes sulfur insoluble. It really depends.
Because according to the trend, that would be insoluble.
Yeah. Let's just go with insoluble in that case.
So would nickel cyanide be insoluble?
So nickel is what kind of element? Transition. In that case, it's not listed under our important exceptions, so it will remain insoluble. Okay. Transitions are typically where exceptions occur. So just be careful of those. Okay. Again, moving forward, let's do some balancing of equations. So if we want to balance equations, how should we go about it? It's a great question. Is it hydrogens first? So hydrogens, since they can break up, we don't want to do those necessarily first. In this case, we want to look at our elements that are only in one compound on both sides. So in this case, a good one to look at would be our nickel and also our carbon nitrate bond. So our nickel is the same on both sides as of right now. How about our carbon and nitrogen bond? No, it changes. So for our carbon and our nitrogen, we want to multiply it by how much? So we multiply this entire thing by 2 to get 2 on both sides. And then we'll have to look at our nickel. Is it still the same? Yes. So as of right now, we don't have to change our nickel. Next, how about what else moves together? So our sulfate, in this case, it goes over the hydrogen. However, it moves together. So SO4 and SO4 on both sides. So we don't have to worry about that. How about, so what's left? So the only thing we haven't considered is our hydrogen. However, with our earlier balancing, we have 2 and 2. So if all of them are equal on the same side, is it a balanced equation? Yes, because now it's equal. So in that case, 2, 1, 1, 1 is how we're going to balance that equation.
If you run into the issue where you can't balance it, the rules just double it, right?
So that's right. So if we can't balance it, if like for some reason we can't get our numbers to add up, typically we're going to want to double everything. Okay? So again, we're going to balance our equations. What element is always in one compound? Is oxygen in one compound? No. So in this case, we're going to want to start with our carbons. So we have 2 on this side. So what should we do to our carbon dioxide? So we should double this to get 2 carbons on both sides. Now we're going to want to look at our number of hydrogens. In this case, how many do we have? 4. So we want to double our water. So now if we go ahead and count up all of our oxygens, in this case, we have 4 for our reactants and 6 for our products. So what should we change? Double our diatomic oxygen, which will now give us 6. So now everything is equal, and that gives us C as our answer for 1, 2, 2, 2. Okay, so again, always start off with the element that's the same number on both sides. Moving forward with our types of reactions, we had our solubility rules. We also had our acid-base reactions, which in the case of our acid typically gives off our hydrogen or a proton. And then our base typically gives us our hydroxide or accepts our proton. In that case, these reactions are also considered neutralization. In our neutralization reaction, what should our products be? Salt and water. The important thing to note is our water will be a liquid. So in the case of our example earlier where our solid remained the same throughout our ionic equations, we'll want our water to stay the same because it's no longer an aqueous, it's now liquid. Okay? Moving forward with that. Yes?
Isn't it electrons only, not protons? Or is it?
So H plus, does that have an electron?
Nope.
Nope. So that's a proton. If we're giving an acid, gives us an H plus, it's giving us a proton. Okay? All right. We also dealt with redox reactions, where that deals with the movement of electrons. Oxidation is loss, and reduction is gain. So that's where we get our oil rig from. We have some rules to assigning those oxidation numbers. Typically, we'll go along with what we have as a charge, with the few exceptions. In the case, oxygen deals with a change when it combines with hydrogen, and hydrogen can deal with a change when it's dealing with a nonmetal. Okay? So we'll get to a question like that where it asks about it in a minute. If we want to look at question number 24, what reaction is occurring in this balanced equation? What type of reaction is it? So it's a precipitation reaction. And we're asking what precipitant forms from this reaction. So Li2SO4 is what forms. So this will become a solid in our products. However, that's not correct. Yeah, our mercury bromide is what forms a precipitant. I'm sorry. In the case, our reactants also actually has a solid. In that case, that's when we have our sulfate. However, one of the things, always slow down to read your questions for her class. She likes to trip you up with how she'll word some of them. And so in this case, it's asking what reaction occurs, not where the precipitant is. Okay? So in that case, the mercury sulfate is already a precipitant. What we're forming is our mercury bromide. And from the equation above, if we want to consider our spectator ions, what would make a compound a spectator ion? Isn't necessarily so straightforward. So it stays aqueous. It needs to remain aqueous, okay? Also needs to remain aqueous on both sides, typically. And in that case, if we want to consider our strong acids mixed with a strong base that forms a salt and water, again, what do we call this reaction? A neutralization. And one thing to note with our acids and bases, how many strong acids are there? And how many strong bases? Those don't really have a necessary pattern to them, so it's just memorization. In this case, which is a strong acid from HCl? And how about NaOH? And how about our C compound? What is that? This is actually a weak acid. And this is why it's important to know your polyatomic ions, because it forms CH3COO negative. Okay? Yes? Strong bases. Otherwise, at that point, we'll have 15 strong acids. And it's just ridiculous. All right. So if we go back to our redox reactions and considering our rules, if we want to denote our oxidation numbers for all of our elements, what will our chlorine be on our reactant side? Okay, thank you. 0. So on the case of our product side, what should also be 0? RBr2, because it's considered its elemental state. In that case, how about our sodium on our reactant side? What are we going to get? So we get a +1. How about our bromine? 1 minus. And then for our products, our sodium is going to be +1, and our chloride is going to be 1 minus. So in that case, our bromine goes from -1 to 0. So what's happening? So that's losing an electron. And how about our chlorine? It's the gaining electron. So in that case, what is being reduced? Our chlorine. One thing to note, our oxidizing agent is what's going to be reduced, whereas our reducing agent would be what? Oxidized, correct. So in the terms of our agents, it's the opposing. It's what's letting, the oxidizing agents what's letting the reducing happen, or our reducing agents what's letting our oxidation happen, okay? So we also then moved into energy, which typically refers to our joules. We also then had to deal with exothermic and endothermic. This is considering what's happening from our system to our surroundings. Our energy also has to deal with kinetic energy, which in the case of our V here, that's V is velocity. Although we don't typically use that equation. Our important equations are pretty much from our relationship of internal energy down to our calorimetry and our standard enthalpy, which our standard enthalpy also has to relate with Hess's law. Okay? So, important to note, our difference in coffee cup calorimetry and our bomb calorimetry is the usage of our mass. In our calorimetry for the coffee cup, we're using specific heat, which uses mass, whereas our C for our bomb calorimetry is heat capacity. That does not use mass. Okay. Also note with our standard enthalpy is very similar to if we're using bond structure. Okay, so in that case, if we wanted to relate this to our bond structures, that would be bonds what minus, right, so bonds broken minus bonds formed. If we apply kinetic energy, yeah?
Oh, I have a question.
Yeah.
For the bomb calorimetry, isn't it negative half for CW?
So, bomb calorimetry, while we can see it with negative, we have to consider where the heat is going. If it's being released, then our bomb calorimetry will be negative. If it's being absorbed, then it'd be positive. So, it's not always negative. We have to consider it in terms of our system. Okay. So, going back from the following, which is an example of kinetic energy. It's actually D because he is currently running. When we're hitting a wall as a molecule, it's momentarily stopping. Okay? How about if we want to consider exothermic reaction? What are we going to get? So our exothermic is energy releasing. So which is an example of it from the given? It'll be B, which is combustion. All of the others are endothermic. Okay? Definitely review the differences in those. That can be tricky, especially I know a lot of people have a problem with the state transitions. So definitely review that. If we want to apply our equations, on this page, note there are a few corrections that I had to make. The uploaded document online has the corrections for the answers. I'll go over those as we get to them. For number 31, what's the equation for delta E? So Q plus W. How about delta H? So while we like to think of delta H, the long technical term is delta E plus pressure in the change in volume. However, if we want to consider it in terms of Q and W, that will cancel this out, as well as our work. So our delta H will end up looking as our Q, okay? In similar concepts, that's what happens with our calorimetry. So that's why our calorimetry is always Q equals, in the case of our equations earlier, MCAT or CAT, okay? So if we want to apply these, we have 4,512 joules for our heat, which is Q, and 37 joules for our work, if we're going with our delta E first. Should those be negative or positive values? So that should be negative, as how about our work? So our work should also be negative. Okay. So in that case, we add them together, and that gives us negative 4,549. However, if we're looking at H, if we're just considering our Q, that's 4,512 joules. And should that be positive or negative? It'll still be negative in this case because our gas is giving off and our system is doing the work. Okay? Does the work. In that case, that's why both of our values are negative, which gives us C for our answer. Okay? So real quick, we'll go to number 33 as to true or false if work has a positive value when work is being done by the system. Or does work have a positive value when being done by the system? False. Again, that's why we have our negative 37 joules, okay? So 32 is a very detailed version of calorimetry. In terms, we want to consider our negative Q of the system equals the positive Q of surroundings. And we also have to take into account our Q is equal to our MCAT. In this case, our specific value, or specific heat values for copper is 0.39, and for water is 4.18. Depending on how many significant figures you use for your specific heat will change slightly the final answer, but it should still be relatively close, okay? If we want to write that entire thing out, our negative Q for our system, we're going to start with copper. So we'll take our mass and our specific heat. And what we want to do is we want to find the final temperature of the container. Using Q, we're doing our change in temperature. So how should this bracket potentially look like? So our temperature final and minus our initial, which in this case has been given to us, 79.8 degrees Celsius. That'll equal the positive value of the similar equation for water, which, again, our mass for water is our 30.9 grams. Our specific heat is 4.18, and we'll get our temperature final minus initial. If we want to do all that math out, we're going to get 9.98 temperature final minus temperature initial on this side, which will give us negative 9.98 temperature final plus 796.4 degrees Celsius on this side. Okay, that's just multiplying everything out. Similarly, on the other side, we'll get 129.16 times temperature final minus initial, which, if we multiply that out, 129.16 TF minus 11,495.24 degrees Celsius. Now, that works out nicely with our distribution of the negatives, because we just have to add them to the other side. In terms, that'll give us 139.14 TF equals 12,291.64 degrees Celsius. From there, we just have to divide. Which is about 88 point something with those significant figures, which is closest to answer A. I'll leave that work up there for a minute. Is there any particular questions about calorimetry in that sense?
The specific thing for copper is just 0.39, which is right?
That was the rounded value.
Okay.
Yeah. So in this case, we're just going with what's given. It's kind of why our significant figure is a little off. Yeah, specific heat will pretty much always be given to you, or you'll have to find it from given values. So you don't have to memorize that, but definitely memorize those equations that help you manipulate for those problems. Is everyone comfortable with that? I mean, after plugging it in, it's just some math, basically. Moving forward with endothermic and exothermic, we have our delta H in terms of products and reactants. So delta H are sigma of moles for the delta H of products minus the delta moles for H of reactants. From this, what do we get for our products? So in that case, it's, again, in this case, if we want to consider the entire value, we have to balance our equation. And that will give us 12 diatomic oxygen, 12 carbon dioxide, and 11 water. All right, so in that case, we have to consider the value for 12 moles of our, starting with the products, so that would be our carbon dioxide, and those values are given to us, so that's 393.5 plus the number of moles for our water, which in that case, negative 483.6. If we multiply those out before continuing, that's 4,722 minus 5,319.6. If we move on to our reactants, that's 1 times our C12H22O11, which that value is still given to us. And we should expect these values to be given to us also on the final exam, plus 12 times our diatomic oxygen, which is 0. So that should just be a positive for our value on the other side. In this case, none of the answers were right. So this was one of the adjusted answers. Our final value should have been negative 7,815.5 joules, which in the case is exothermic, which is none of the above values. Okay? Moving forward with Hess's law, we have to consider our values for and how we would change them. We want to make sure our products and reactants are on the proper side. So in the case of our second equation, what should we do? Our second equation should be flipped around so we can get the right products and reactants. This also was adjusted on the original. The 2 should have been on our calcium, not the oxygen. And then in that sense, we should make this positive, which is one of the rules for Hess's law, that if we flip around the equation, it also flips the sign of our delta H. In order to then cross out and get the proper number of our products and reactants, we can either multiply our top equation by 2 and then divide at the end, or we can simply divide this by 1/2 to give us and some number for our delta H. And in that sense, if we add all of our 2 equations together, do we get our final desired equation? So yes, we should. If you have difficulties with crossing out, I suggest writing the entire thing out and crossing out later. And that'll look like that, which we can then see what's same on both sides and cross those out. And that will give us our final desired equation. So we can then plug in our delta H's. Which (177.9 kilojoules) is what we should end with. All right. Yeah, just seeing as to where we are. So moving forward in terms of electromagnetic radiation, our speed of light and our Planck's constant will be given to us. In the terms of finding energy, we just have to plug in all of our math. So our H times C we'll go over the wavelength, which in this problem has been given to us. And this will be an equation to go back and make sure your calculators are working properly or your fingers are working properly. If you plug all of that in with the proper exponents, that'll give you 3.51 times 10 to the negative 17, which is answer A. Be careful in these problems because typically your wavelength will be given to you in nanometers, and you'll have to be able to convert between nanometers to meters, okay? One thing you want to review is how frequency and wavelength correlate with each other. So in our options below, which has the lowest frequency? Our radio waves. Okay, so make sure you know the general order for that and how that relates to our frequency and our wavelength. So with a greater wavelength, we'll have a smaller frequency. Next important thing to understand is our quantum numbers. Make sure you review those. The chart's been given to you as how those function. So our n being our principal level, our L being our orbital type, and remember L is equal to n minus 1. And our m of L spans from positive L to negative L values, with our spin being plus or minus. That follows with all the rules and how we fill our orbitals. So we can have 2 electrons in each orbital. However, how many electrons can S hold?
2.
So 2. How about P? 6. So it has 3 orbitals, and that's why we have our 6. How about for D? 10. And our F, 14 electrons. And which orbitals constitute our valence electrons? So our S and P are valence. Make sure you review how those fill up the orbitals. And with that, what gives us our electron configuration order. So one thing to note with that is that we have our full electron configuration and our noble gas shorthand. However, for a noble gas, it cannot be its own abbreviation. So again, if we want our neon, we're going to have to write that out. We can't just write neon. So in the case for our mercury, our electron configuration, if we write it all the way out, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. What comes after 4s2? We start adding our Ds, so that'll be our 3d10, 4p6, our 5s2, what's next? 4d10, our 5p6, and then with our 6s, what do we have next? So now we have to go back to 4 for our f, 14, and 5d10. So be careful, our f is going to start for our inner transitions, which will be in 6 and 7, okay? So if we wanted to just shorthand that, we could use xenon 6s2 for f14 and then 5d10. Okay? So moving forward from that, if we just wanted to use the noble gas configuration for selenium, what would we get? So we can go ahead and cross this one out because we're already using a noble gas. And we can't use krypton. So, and then for B, we have to have our S. So our B will be correct, and that's why our D is not correct, because we're skipping our S. Okay? And in terms of that, if we want to figure out our valence electrons and our electron configuration for magnesium, we can still use our periodic table. So what would our valence electrons be for a magnesium? So we can still find that on our periodic table. It'll be in the third column, so that'll be 3s2, giving us 2 valence electrons. If we want to skip orbital levels, which has the highest energy absorption for the photon, we are absorbing if we're moving up in energy levels.
So going down the rows?
So in that case, this is going down by 4. This is going up by 3, down by 1, up by 1, up by 1. So which has the biggest jump? B. Okay? So running through our trends, electron affinity is gaining our electron. And the ability of an atom to gain an electron. This is considered exothermic, usually, and can be written as the atom plus an electron giving you the ion. Okay? And if we go back to our trend, the general increase for electron affinity will increase up and to the right. Okay? Trends, make sure you go a little more in depth on why it's happening, so it'll make more sense answering the questions later on. In terms of atomic radius, our size will increase going left because size increases as our effective nuclear charge decreases.
Is that from left to right or right to left? Going this way across?
So our effective nuclear charge decreases as we go left on the periodic table. Okay? And going down, our atomic radius increases because size increases as the number of orbitals increases. For ionic radius, our cations get smaller or larger? Smaller, and so our anions get larger. Ionization energy is the energy to remove an electron? So it's kind of the inverse of what's happening with electron affinity, except the trend is still the same. So we can write that similarly with our Cl becoming an ion as the electron is released. So that will be endothermic. And our effective nuclear charge in general increases up and to the right as it's our atomic number minus our core electrons, or our protons minus our electrons. Our electronegativity can be quantized using numbers. Those can be given to us or found sometimes on a periodic table, depending on the periodic table given to us. There's also the trend, where it also increases up and to the right. So in terms of our most electronegative for number 42, we should get what? Oxygen. While our bromine is the farthest to the right, it is below our sulfur and our oxygen and nitrogen. So our trend, if we wanted to write it all out, will look like that. In terms of ionization energies, our ionization energies will have a less of gap when we're taking valence electrons. So we have 1, 2, this is our quantum leap. So that'll give us a positive 2 charge indication. So in that case, if we want to give our X a positive 2, our phosphate's still negative 3. So that'll give us D. So the next few are just kind of general trends of the periodic table. Our metalloids will be found along our staircase. So our germanium and arsenic. Our metals will form ions with what? So our metals typically become positive. So they'll be anions that they'll form with. For transition metals, one of the common things we know is that they'll have a different set of charges. So that's why C is the correct answer. Lattice energy is using Coulomb's law. And we're taking into account with charge and our radius. And then moving on from there, we got into how we draw Lewis structures. Those steps are drawn out for us, and how we would take into account if we wanted to make that an ion. With that, we also talked about bond lengths. If we have a single bond, what is that considered? That's a sigma bond as well. So, and then if we're getting into the sigma and pi's, if we have a double bond, sigma and pi, triple bond, sigma 2 pi. Make sure you actually draw the entire structure out in that case for those. And true or false, single bonds take the most energy to break. False. However, if we were to ask if that's a sigma bond, this would be true. Okay? So that's the difference between sigma and pi because of the way they're shaped, remember? So sigma bonds are harder to break, and they'll need more energy to break them, whereas if we're considering just single bonds, it's not. because in the case of double and triple, we still have our single bonds, okay? Or our sigma bonds, if I didn't say that correctly. In terms of polarity, our ranges are given to us with nonpolar, polar, and ionic. This takes into account our electronegativity. And so again, if we want to consider which is most polar between the following bonds, we have to consider the differences in electronegativity. So between H, N, O, and F, which is most electronegative? F. So that should be the farthest difference with our carbon. Hybridization relates to our molecular and electron geometries. I've given you a chart to make sure you go over and memorize. Remember, when we are functioning with that we're taking into account all of our electron pairs. So taking into account SF4, we have how many valence electrons? So we have 6 valence electrons. Each of our fluorines will take one of those, and so we'll be left with 2. So in that case, if we want to count electron groups, remember that's the number of bonds with the number of lone pairs. If you have memorized your chart, which you definitely should, that will give you the fact that your electron geometry is trigonal bipyramidal, meaning 5. So you have 5 electron groups. And your molecular geometry changes in format because of your lone pair. So you have A. Okay? So that's taking into account your lone pairs. That also functions with, real quick, your hybridization and the fact that we, for this molecule, have our central atoms and 2 hydrogens. So what forms in the middle? Triple bonds, because carbon can have 4 bonds, all right? And so with that, how many electron groups does each carbon have? It has 2. It doesn't matter what kind of bond you have, it's always only 1. So a triple bond, a double bond, and a single bond all count as 1, okay? So in that case, you have 2 electron groups, and that will give us hybridization of sp, okay? So in the counting of hybridization, it's basically taking into account that your electron groups are constituting twice as many electrons. So if we were to write that out for electrons, S2, P2, but in terms of hybridization, you're just counting the pairs, so that's why it's S1, P1, okay? Unfortunately, that is all the time that I have. I will open the last few minutes for a couple questions, and I will post the answers for the Lewis structures and the few questions for gases. Make sure you definitely go over the gas laws, okay?
Do you have office hours or something else?
I don't have,
No, I know you don't. But
yeah.
somebody does.
Hyder should, and there are some in the chem building.
Okay.
Yeah, those should be on her lecture slides if you need to find those.
I heard this like earlier last week, so it's different from the one that you had, like
A lot of the questions are the same.
the same. So
I've just basically added a lot of outline words.